Place a glass on the edge of a table. Push it gently. Watch it fall to the floor and shatter. You have just witnessed something that, by every fundamental equation in physics, should be reversible. The pieces of the glass on the floor could, in principle, reassemble themselves. The shards could leap upward. They could fit themselves back together along their original fracture lines. The reformed glass could rise from the floor and come to rest on the edge of the table. Every law of motion that governs the original fall permits the reverse process. There is no equation in physics that forbids it. It does not happen. You have never seen it happen. Nobody you know has ever seen it happen. In all of recorded human history, no person has ever witnessed a shattered glass spontaneously reassemble itself. The reverse process is, by fundamental physics, allowed. The reverse process is, by every observation, absent. This is the asymmetry we are going to spend the next 2 hours with. Eggs break and do not unbreak. Smoke rises and disperses and does not gather itself back into a flame. Sugar dissolves in coffee and does not, of its own accord, reassemble into a cube. Footprints in sand persist for a while and slowly fade and never undo themselves into the pristine surface that preceded them. Memory accumulates of yesterday and not of tomorrow. The bodies of the living age toward dissolution and not back toward youth. Every one of these directional behaviors is, by the fundamental equations of physics, unnecessary. Newton's laws of motion work equally well played forward or played backward. Maxwell's equations governing electromagnetism are symmetric under time reversal. The Schrödinger equation of quantum mechanics is symmetric. Even general relativity, our deepest theory of gravity and the fabric of space-time, is symmetric to a high degree of precision. The equations do not contain a preferred direction of time. They permit all the reverse processes that we never observe. They are, in their mathematical structure, agnostic about whether the past is before us or behind us. The universe is not agnostic. The universe has chosen a direction. The choice is consistent. The choice is universal. The choice applies to every process anywhere in the cosmos that we have ever been able to observe. The choice does not come from the equations. The choice comes from somewhere else. We do not know where. That is what we are going to sit with. Not a peculiar anomaly, not a strange observation. The deepest asymmetry in physical reality, the difference between past and future, sits in the universe without any clear basis in the laws that supposedly govern everything. The asymmetry is real. The asymmetry is constant. The asymmetry has been operating since the universe began. Whatever set it up did its work in a regime we cannot directly study, and the consequences have been propagating ever since. You are inside the propagation. Your sense that this moment is now, that a moment ago is past, that a moment from now is future, that sense is the asymmetry expressing itself in your awareness. The asymmetry produces what we experience as time itself. The experience is so basic to consciousness that we rarely examine it. The examination, when conducted, reveals that the foundation of the experience is not in the equations of physics. The foundation is somewhere we have not yet located. Take a slow breath. We will walk through this carefully. We will look at what time reversal symmetry actually means in the fundamental equations. We will see how the second law of thermodynamics introduces direction. We will examine why the second law cannot be the ultimate source. We will arrive at a hypothesis that places the source of time's direction not in the laws of physics, but in the initial conditions of the universe itself. We will see why that hypothesis, while widely accepted, does not actually resolve the question. It only relocates the question to a place we cannot examine. Move slowly. The territory is unfamiliar even to people who have studied physics for years. The strangeness rewards patience. We begin with what time reversal symmetry actually says. Take any of the foundational equations of physics. Newton's second law, force equals mass times acceleration. Pick a physical system, say a pendulum swinging back and forth. Solve the equation. you get a description of how the pendulum moves over time. The position of the pendulum at any moment can be calculated from its position and velocity at any other moment. Now perform a specific operation. Take the equation and replace every occurrence of time, t, with negative time, minus t. This is the mathematical operation of time reversal. It corresponds, intuitively, to running a film of the system in reverse. Look at what the equation does. The acceleration term, which involves the second derivative of position with respect to time, contains two factors of t. When you replace t with minus t, the two negative signs cancel. The acceleration term is unchanged. The forces, in most cases, depend only on positions which are also unchanged under time reversal. The equation, after the substitution, looks exactly like the original equation. This means that if a particular motion satisfies Newton's law, the time-reversed motion also satisfies it. The reverse process is allowed by the law. The law does not distinguish between the original and the reverse. This is sometimes called the principle of microscopic reversibility. Every physical interaction between particles, considered in isolation, can run in either temporal direction without violating any fundamental rule. Two particles approaching each other, colliding and recoiling. This is a valid sequence under the laws of motion. The same sequence in reverse, two particles approaching each other, colliding in the same way and recoiling, is also a valid sequence. The laws do not specify which direction was the original and which was the reverse. The principle was first carefully analysed by physicists in the 19th century as they worked out the mathematical structure of mechanics. James Clerk Maxwell understood it. Ludwig Boltzmann understood it. Henri Poincaré understood it. The principle was, by the late 1800s, well established in the foundational mathematics of physics. The principle's apparent conflict with everyday experience was also recognised. The community knew that everyday phenomena seemed irreversible. They knew that the equations did not require any irreversibility. The community spent the late 19th and early 20th centuries trying to reconcile these two facts. The reconciliation produced the modern understanding of entropy and the second law, which we will examine in detail later in this video. The same operation can be performed on other fundamental equations. Maxwell's equations governing electricity and magnetism, the Schrödinger equation governing the quantum behavior of particles, the equations of general relativity describing the geometry of space-time. With minor exceptions and subtleties, each of these is symmetric under time reversal. The processes they describe can be run in either temporal direction, and the equations remain satisfied. Maxwell's equations describe how electric and magnetic fields evolve and interact with each other and with charged matter. The equations involve time derivatives of the fields. When you reverse time, certain quantities change sign. Magnetic fields flip direction, for instance, since they are produced by moving charges and the motion reverses, but the equations as a whole remain satisfied. A configuration of fields and charges that is allowed by Maxwell's equations has a time-reversed counterpart that is also allowed. The radiation from a charged particle moving in one direction has its mirror image in radiation absorbed by a charged particle moving in the reverse direction. The Schrödinger equation, which governs the wave function of a quantum system, also has a time reversal symmetry, though the symmetry involves taking the complex conjugate of the wave function in addition to reversing time. The combined operation produces an equation that looks like the original. Any quantum evolution that is allowed forward in time has a reverse counterpart that is also allowed. The puzzle of quantum measurement aside, the underlying dynamics of quantum mechanics do not specify a preferred direction of time. General relativity describes how matter and energy curve space-time, and how the curvature in turn governs the motion of matter and energy. The equations are notoriously complex, but they too possess time reversal symmetry under appropriate conditions. A solution describing the formation of a black hole from collapsing matter has a time-reversed counterpart describing the expansion of a white hole into outgoing matter. The white hole solution is allowed by the equations. It is also, in the universe we observe, never seen. The asymmetry between black holes and white holes is one of many specific instances of the broader arrow of time problem. There is one minor exception worth noting. The weak nuclear force, one of the four fundamental forces, shows a small asymmetry under a specific combined operation called CPT, charge conjugation, parity, and time reversal. The asymmetry has been measured in certain particle decays. It is small. It is not, by itself, the origin of the macroscopic time asymmetry we observe in daily life. The CPT asymmetry of the weak interaction operates at energies and scales that do not directly produce the directionality of broken glasses or scattered ashes. Whatever causes the macroscopic arrow of time, it is not the CPT asymmetry of the weak force. The weak interaction asymmetry is, however, important in its own right. It was discovered in the 1960s by James Cronin and Val Fitch in experiments studying the decay of kaons. The discovery was unexpected. Before that point, physicists had assumed that the fundamental laws would be exactly symmetric under appropriate combined operations. The discovery that nature does, at a small level, distinguish between processes and their time-reversed counterparts opened a new line of inquiry. The inquiry has continued. It has produced refined measurements of the asymmetry. It has not, so far, identified a mechanism by which the small asymmetry of the weak interaction could account for the much larger asymmetry of everyday experience. So the fundamental equations are essentially symmetric under time reversal. Yet the universe is manifestly not symmetric. The asymmetry is everywhere. The asymmetry is in every cup of cooling tea, in every footprint on a beach, in every memory you have ever formed and failed to form in advance. How is this possible? Where does the directionality come from if not from the equations? The traditional answer in physics is the second law of thermodynamics. This is where we walk slowly. The second law is one of the most discussed and least understood statements in all of physics. It is taught in every introductory thermodynamics course. It is also the source of profound philosophical puzzles that have not been resolved in 2 centuries of careful work. The second law states, in its most common formulation, that the entropy of an isolated system never decreases. Entropy is a measure of the number of microscopic arrangements consistent with a given macroscopic description. A system with low entropy has few microscopic arrangements available. A system with high entropy has many. Over time, systems left to themselves move from configurations with few accessible microscopic states to configurations with many. This is the second law. The historical development of the second law is worth tracing briefly. The concept of entropy was introduced by Rudolf Clausius in the 1860s, originally as a thermodynamic quantity related to heat flow. Clausius noticed that, in any spontaneous process, a certain combination of heat and temperature could only increase or stay the same. He called this quantity entropy. The name was chosen by analogy with energy. Clausius defined entropy in terms of measurable thermodynamic variables. The definition was operational. It worked for engines and refrigerators and gas expansions. It did not, by itself, explain why entropy increased. The deeper explanation was provided by Ludwig Boltzmann in the 1870s and 80s. Boltzmann worked out the statistical foundation of thermodynamics. He showed that entropy could be understood, microscopically, as a count of the number of ways a system could be arranged at the molecular level while still presenting the same macroscopic appearance. A gas occupying half a container has fewer molecular arrangements available than the same gas spread uniformly throughout the container. The uniform configuration is, in this sense, higher entropy than the half-empty configuration. Boltzmann's contribution was to derive the second law from this microscopic picture. He showed, with various technical caveats, that systems composed of many molecules would, when left to themselves, tend toward configurations with more molecular arrangements available. The tendency was not absolute, fluctuations were possible, but for macroscopic systems with vast numbers of molecules, the fluctuations were too small to observe. The systems appeared to obey the second law with extraordinary precision. Boltzmann's work was met with considerable resistance. Some of his contemporaries argued that his derivation was circular, that he had implicitly assumed a kind of randomness or directionality in his statistical analysis, and that the directionality was then producing the second law as a consequence. The debates were intense. Boltzmann defended his work for decades. He committed suicide in 1906. The full implications of his ideas were worked out by others in the subsequent decades. By the early 20th century, the statistical interpretation of entropy was largely accepted. The second law was understood as a statistical regularity that emerged from molecular dynamics. It was not a fundamental law in the same sense that Newton's laws or Maxwell's equations were fundamental. It was a derived statement about the behavior of large collections of molecules. Consider what entropy means in concrete terms. Take a deck of cards arranged in perfect order, all the suits separated, each suit in numerical sequence. This is a configuration with very low entropy. There is essentially one arrangement of the cards that satisfies the description. Now shuffle the deck thoroughly. The result is a configuration with very high entropy. There are astronomical numbers of arrangements that all look like a thoroughly shuffled deck. They are all approximately equally disordered, and from a description like thoroughly shuffled, no specific arrangement can be picked out. The deck does not, by itself, return to ordered configuration. Shuffling does not reverse itself. The reason is statistical. There is only one ordered configuration. There are roughly 80 unvigintillion shuffled configurations. The number of shuffled arrangements is so vastly larger than the number of ordered arrangements that, if you simply shuffle randomly, you will spend essentially all your time in the shuffled region of configuration space. The probability of stumbling into the ordered configuration by random shuffling is so small that, in any practical time frame, it will not happen. This is the second law in microcosm. Systems evolve from low entropy configurations to high entropy configurations because there are vastly more high entropy configurations than low entropy configurations. The evolution is not driven by any directional force. It is driven by the asymmetry of the configuration count. There is nowhere else to go. The second law, applied broadly, explains why eggs do not unbreak. An intact egg is a configuration with low entropy. The molecules of the egg are arranged in specific structures of shell, white, and yolk, each in their proper relations. A broken egg is a configuration with high entropy. The molecules are scattered, the structures dispersed, the relations randomized. There are vastly more ways to arrange the molecules in the broken configuration than in the intact configuration. So broken eggs persist. Intact eggs, given enough time and disturbance, break. The reverse process is statistically forbidden. The same explanation extends to every other apparent asymmetry in daily experience. Heat flows from hot to cold because the hot-cold configuration has lower entropy than the uniform temperature configuration. The flow proceeds because there are more states corresponding to uniform temperature than to separated temperatures. Memory accumulates because the act of recording a memory increases the entropy of the recording system. Causation runs from past to future because causes are typically lower entropy events that produce higher entropy effects. For a moment, this looks like a complete answer. The second law of thermodynamics gives time a direction. The direction is from low entropy to high entropy. The universe began at low entropy and is moving toward high entropy. The arrow of time is just the entropy gradient extended over cosmic history. But there is a problem with this answer. Sit with it carefully. The problem is not obvious until you examine the statistical foundation of the second law. The second law, as just described, is a statistical statement. It says that systems tend to evolve toward configurations of higher entropy because higher entropy configurations are more numerous. But the underlying dynamics, the equations of motion that govern the molecules in any system, are symmetric in time. The molecules do not know they are supposed to be increasing entropy. They simply follow the equations. Here is the puzzle. If the equations are symmetric in time and the molecules follow the equations, then a system that evolves from low entropy to high entropy in the forward direction should also evolve from low entropy to high entropy in the backward direction. The reasoning goes, pick any moment in the system's history. Look at the molecular configuration at that moment. The configuration is overwhelmingly likely to lie in the high entropy region of configuration space, because high entropy regions contain almost all the configurations. From that configuration, run the equations forward in time, and the system will tend to remain in or move further into the high entropy region. But also from that same configuration, run the equations backward in time, and by the same statistical reasoning, the system should tend to remain in or move further into the high entropy region. In other words, statistical mechanics, applied symmetrically, predicts that entropy should increase both into the future and into the past from any current moment. This is sometimes called the reversibility paradox, or Loschmidt's paradox, after the 19th century physicist Joseph Loschmidt, who first articulated it as an objection to Boltzmann's work. Loschmidt's point was straightforward. If the underlying dynamics are time symmetric, then any process producing entropy increase must have a time-reversed counterpart producing entropy decrease. The two processes should be equally likely by the symmetry of the laws. The observed fact that we see only entropy increase requires explanation that goes beyond the laws themselves. The paradox is sharp. It cannot be dissolved by appeal to randomness alone, because the underlying dynamics are not random. They are deterministic and time symmetric. It cannot be dissolved by appeal to large numbers alone, because large numbers respect the symmetry of the underlying dynamics. The paradox requires, for its resolution, some assertion about the universe that goes beyond what the dynamical laws say. Boltzmann himself recognized this. His response, late in his career, was to suggest that the universe might be in an overall equilibrium state, with the observed entropy gradient being a local fluctuation. Within the fluctuation, observers like us experience entropy increase in one temporal direction. Outside the fluctuation, the universe is in equilibrium and has no clear arrow of time. The observed asymmetry is then a feature of the fluctuation we happen to inhabit rather than a feature of the universe as a whole. This proposal has its own problems, which we will examine later. For now, what matters is that Boltzmann recognized the depth of the issue. The second law of thermodynamics, as a consequence of time-symmetric dynamics applied statistically, cannot produce a one-directional arrow of time. Something more is needed. This is not what we observe. We observe entropy increasing only into the future. The past, when we examine it through memory or records, contains configurations of lower entropy than the present. Yesterday's coffee was hotter. Last year's mountains were less eroded. The Earth, a few billion years ago, was hotter and more chemically active. Entropy in the past is observed to be lower than entropy in the present, in a consistent pattern that contradicts what naive statistical mechanics would predict. How is this possible? How does the entropy of the past come to be lower than the entropy of the present when the equations of motion treat the two directions symmetrically? The answer, when it was worked out by Ludwig Boltzmann and his successors, was uncomfortable. The answer is that the entropy of the past is lower, not because of any dynamical law, but because of the initial conditions of the universe. This is where we cross into the heart of the puzzle. We have moved through the symmetric equations, the statistical second law, and the observation that statistical reasoning alone does not produce one-directional entropy increase. We arrive at the proposal that one-directional entropy increase requires an asymmetric input. The input is the state of the universe at its beginning. The proposal has a name. It is called the past hypothesis. The past hypothesis states that the universe began in a state of extraordinarily low entropy. Not just somewhat low, spectacularly low. The initial entropy of the universe was so far below the typical entropy that statistical mechanics would predict for a random configuration that the universe has been doing nothing since the moment of its beginning, except evolving toward higher entropy configurations. The arrow of time is the visible expression of this initial improbability gradually playing itself out. Walk slowly through what this means. The universe, at the moment of the Big Bang, was in a state that, by every measure of statistical likelihood, should not have occurred. The probability of a randomly selected initial state having entropy as low as the actual initial state of our universe has been calculated. The result is a number so small that it requires special notation to write down. 1 in 10 to the power of 10 to the power of 123. The number of zeros in the denominator is itself larger than any quantity in human experience. The calculation was performed by Roger Penrose. Penrose has emphasized the extraordinary improbability of the universe's initial state in much of his writing. He has argued that the past hypothesis represents one of the deepest unexplained features of cosmology. The number Penrose calculated, 1 in 10 to the 10 to the 123, is so small that if you wrote out the denominator as a standard decimal number, you could not write it within the observable universe. There are simply not enough particles in the cosmos to write down the digits. This level of improbability is not normal. Most physical configurations are statistically typical. They are drawn from the vastly larger regions of configuration space where typicality lives. The initial state of our universe was drawn from a region so small that finding it by chance is unimaginably rare. Yet the universe was, somehow, in that region. The how of this remains an open question. The universe began at this improbable starting point. From that starting point, all subsequent evolution has been a gradual approach to more typical higher entropy configurations. The approach has been ongoing for 13.8 billion years. The approach has not yet been completed. The universe is still very far from the maximally high entropy state it will eventually reach. To get a feel for how far the universe still has to go, consider the eventual state of the cosmos. Over enormous timescales, far exceeding the current age of the universe, stars will exhaust their fuel and become dim remnants. Galaxies will eject most of their stars through gravitational interactions, becoming sparser and quieter. Black holes will form from the remains of the largest stars and from the cores of dead galaxies. Eventually, even black holes will evaporate through Hawking radiation, releasing their mass energy as low-frequency thermal radiation. The universe, after these enormous timescales, will consist of nothing but extremely diffuse radiation and a small population of stable particles distributed thinly across an enormously expanded volume. This is the heat death. The heat death represents the maximum possible entropy for our universe. The entropy at heat death is far higher than the entropy of the current cosmos. The difference is large enough that, by some measures, we are still in the very early stages of the universe's approach to maximum entropy. Most of the entropy increase that will ever occur is still in our future. We are, in this sense, living in a universe that is still extraordinarily ordered compared to where it is headed. The current ordered state is what makes life possible. Life requires low entropy energy sources, typically the gradient between the sun's surface and the cold of space, to drive the biochemical processes that constitute living systems. Without the entropy gradient, there would be no flow of energy through living things, and there would be no living things. The arrow of time is, in this very direct sense, the precondition for biology. Without it, no metabolism. Without metabolism, no life. Without life, no observers. In the meantime, while the approach continues, every process within the universe inherits the directional character of the overall entropy increase. Local processes, the cooling of coffee, the dispersal of perfume, the formation of memories, all proceed in the direction of higher entropy because the universe as a whole is proceeding in that direction. The local processes are not generating the arrow of time. They are reflecting the global arrow that the past hypothesis establishes. This explanation has been the dominant framework in physics for understanding the arrow of time for over a century. It originated with Boltzmann in the late 19th century. It has been refined by many thinkers since. The cosmological version, in particular, has been developed by physicists including David Albert, Sean Carroll, and others. The past hypothesis is widely accepted as the best available account of why time has a direction. But the past hypothesis does not actually resolve the question. It only relocates it. Sit with what comes next slowly. The relocation is the heart of the puzzle. The past hypothesis says that the universe began at very low entropy. It does not explain why. The dynamical laws of physics do not require any particular initial state. The equations are symmetric in time and indifferent to the entropy of any configuration. If you pick a random initial state and run the equations, the resulting universe will, on statistical grounds, look approximately uniform in entropy in both temporal directions. There is nothing in the equations that prefers a low entropy beginning. The low entropy beginning is therefore an additional fact about our universe, a fact that is not derivable from the laws. It is a boundary condition, a specification of how the universe started, separate from the rules that govern how it evolves once it has started. The boundary condition is enormously fine-tuned. The boundary condition has no explanation within the physics we currently know. The arrow of time in the past hypothesis framework is not produced by the laws of physics. It is produced by the boundary condition. The boundary condition is unexplained. The arrow of time is therefore, by this analysis, unexplained at its deepest level. This is uncomfortable. Most physical phenomena are explained by appealing to the laws. We say that water flows downhill because gravity pulls it downward. We say that magnets attract iron because of electromagnetic forces. We say that planets orbit the sun because of the curvature of spacetime described by general relativity. In each case, the law provides the explanation. The phenomenon is a consequence of the law. The arrow of time in the past hypothesis framework is not a consequence of any law. It is a consequence of a specific initial state. The state is itself not explained by any law. The arrow of time hangs, in this framework, on a fact about the universe's beginning that is itself a brute fact. There have been many attempts to push the explanation deeper. The community has explored whether some additional physical principle might explain why the universe began in low entropy form. The exploration has not produced consensus answers. The proposals have been creative. None has been confirmed. We will walk through some of them. The first major attempt to explain the low initial entropy invokes cosmic inflation. Inflation is the proposed period of extremely rapid expansion in the very early universe, occurring in the first tiny fraction of a second after the Big Bang. The inflationary expansion was vastly faster than the expansion the universe has experienced since. During inflation, a small region of space, originally smaller than a proton, expanded by an enormous factor, possibly by more than a factor of 10 to the 26th, in less than a tiny fraction of a second. Inflation was proposed in the early 1980s as a solution to several problems in standard cosmology. The horizon problem, the flatness problem, the monopole problem. Each of these was difficult to address without invoking some kind of early rapid expansion. Inflation, by providing the expansion, solved several problems simultaneously. The original inflationary proposal came from Alan Guth in 1981. Guth was working on problems in particle physics, specifically on the question of why we do not observe magnetic monopoles in the universe despite their predicted production in the early hot phase. He found that a brief period of exponential expansion could dilute any pre-existing monopole density to undetectable levels. The mechanism turned out to solve other problems as well. The horizon problem, the puzzle of why distant regions of the cosmic microwave background have the same temperature, could be solved if those regions were once in causal contact before being separated by inflationary expansion. The flatness problem, the puzzle of why the universe's spatial geometry is so close to flat, could be solved if inflation drove any initial curvature towards zero. Inflation was refined by subsequent theorists. Andre Linde, Andreas Albrecht, Paul Steinhardt and others developed variations and improvements. By the late 1980s, inflation was widely considered the standard framework for understanding the very early universe. Subsequent observations of the cosmic microwave background, particularly the precise measurements from WMAP and Planck, provided detailed support for many inflationary predictions. The community moved into a state of broad acceptance of inflation as a general framework, though the specific implementation, what kind of field drove the inflationary expansion, how exactly it started, how it ended, remains disputed. One feature of inflation is relevant to the arrow of time. The inflationary expansion would have driven the universe toward a particular kind of smooth, uniform configuration. The smoothness and uniformity that we observe in the cosmic microwave background and that we observe in the large-scale distribution of matter can be traced back to the smoothness that inflation produces. The smoothness, in some analyses, can be characterized as a kind of low entropy state. So perhaps inflation explains the low initial entropy. The universe began with whatever entropy it had at the Big Bang. Inflation then drove it toward a particularly smooth configuration. The smooth configuration is, in some respects, low entropy. Subsequent gravitational evolution has been moving away from the smooth configuration into configurations with more clumping and more structure. The motion away from smoothness is, in this picture, motion toward higher entropy. The arrow of time is the direction away from the smooth post-inflationary state. This explanation has appealed to many cosmologists. It has the virtue of connecting the arrow of time to a well-developed cosmological mechanism. It potentially explains why the early universe was smooth without invoking an unexplained boundary condition. The explanation has problems. We need to walk through them carefully. The first problem is conceptual. Inflation is itself a dynamical process. It is governed by equations. The equations, like other fundamental equations of physics, are essentially time-symmetric. If inflation can produce a smooth state by running forward, the time-reversed inflation could also produce a smooth state by running backward. The process does not contain its own directionality. The directionality has to come from somewhere else. The second problem is the question of what came before inflation. Inflation, in standard cosmological models, was a phase that the universe entered and then exited. Before inflation, the universe was in some other state, call it the pre-inflationary state. The pre-inflationary state was the starting condition from which inflation began. What was the entropy of the pre-inflationary state? If the pre-inflationary state had high entropy, then inflation would have had to produce a low entropy state from a high entropy one. This would itself be a decrease in entropy, which is the kind of process the second law forbids. So if the second law applies during the pre-inflationary epoch, the pre-inflationary state must have had low entropy, at least as low as the post-inflationary state. But if the pre-inflationary state already had low entropy, then we have not actually explained the low initial entropy. We have only pushed it back one step. The pre-inflationary state requires its own explanation. The arrow of time problem retreats one level but does not dissolve. The third problem is that there is no earlier time we can study. Our observational access to the early universe is limited. We can study the cosmic microwave background, which dates from approximately 380,000 years after the Big Bang. We can study the relative abundances of light elements, which date from a few minutes after the Big Bang. We have indirect evidence from various sources about earlier moments, but the pre-inflationary state, if it existed, occurred earlier than any observational evidence can reach. We cannot directly determine its entropy. We cannot directly determine its properties. We can speculate, but speculation is not the same as evidence. So the inflationary explanation, while attractive, does not actually resolve the past hypothesis problem. It accepts that some low entropy state existed before inflation and offers no account of where that state came from. There have been other attempts. One line of thinking involves quantum cosmology and the wave function of the universe. The Hartle-Hawking proposal and various successors suggest that the universe's initial state can be specified by a particular kind of quantum boundary condition, typically a no-boundary condition in which the universe simply emerges from a state that lacks a sharp temporal beginning. In some formulations, this approach can be combined with assertions about the initial entropy. The combination is, in principle, capable of producing a universe with a low entropy starting condition. The quantum cosmology approach has its own difficulties. The mathematical structure is intricate. The interpretation of the results is contested. Whether these proposals genuinely explain the low initial entropy or merely encode it in different mathematical form is a matter of ongoing debate. The community has not converged on a definitive view. Another line of thinking involves the possibility that our universe is part of a larger multiverse, in which different regions have different initial conditions and different entropy gradients. In some versions of this picture, the past hypothesis is not a special fact about our particular universe, but a consequence of observation selection. We exist in a region of the multiverse with a particular entropy gradient, because regions without entropy gradients cannot support observers like us. The arrow of time is a feature of our local cosmic neighborhood rather than of the multiverse as a whole. This line of thinking has the same problem as anthropic explanations elsewhere in physics. It explains why we observe what we observe, but does not explain why the relevant configurations exist at all. If the multiverse contains regions with all possible initial conditions, the explanation for the past hypothesis is essentially that we happen to be in one of the regions where the past hypothesis happens to hold. The hypothesis remains true. The deeper question of why such regions exist remains open, so we have walked through the standard answers. The second law of thermodynamics gives a statistical account of why entropy increases. The past hypothesis says that the increase requires a low entropy initial state. The inflationary explanation, the quantum cosmology approach, and the multiverse approach attempt to derive or justify the past hypothesis from deeper principles. None of these attempts is fully successful. The arrow of time remains, at its deepest level, an unexplained fact about the universe we inhabit. There is a further consideration that deepens the puzzle. The arrow of time is not a single arrow. There are many arrows pointing in the same direction. Physicists have catalogued several distinct arrows of time, each operating in a different domain, and the alignment of all of them in the same direction is itself a fact requiring explanation. The thermodynamic arrow is what we have been discussing. It is the arrow of entropy increase. Systems left to themselves move toward configurations of higher entropy. This is the most fundamental arrow in most analyses. There is also a psychological arrow. We remember the past and not the future. Our experience of time has a built-in directionality that distinguishes memory from anticipation. The psychological arrow is, almost certainly, downstream of the thermodynamic arrow. The brain's process of forming memories involves chemical changes that increase entropy. Memory itself is a record of past entropy gradients. The reason we cannot remember the future is that the future has not yet sent us its entropy traces. The psychological arrow inherits from the thermodynamic arrow. There is a cosmological arrow. The universe is expanding. Galaxies are receding from each other on average. The expansion is, in our local cosmic neighborhood, accelerating due to dark energy. The expansion picks out a direction, the direction in which the universe is getting larger, hotter only in certain regions, and structurally more dispersed at large scales. The cosmological arrow is, by some accounts, related to the thermodynamic arrow through the way that gravitational systems organize themselves. But the two arrows are not obviously the same arrow. The question of why they align in the same direction is itself an open problem. There is a radiation arrow. Electromagnetic radiation from a source spreads outward in expanding wavefronts. The wavefronts move away from their sources, not toward them. We do not, in everyday experience, observe converging wavefronts spontaneously condensing into a single emitting point. The radiation arrow is, in this respect, distinct from the thermodynamic arrow, though it is likely related at a deep level. There is a quantum arrow associated with the measurement process. When a quantum measurement occurs, the wave function appears to collapse to a definite outcome. The collapse is irreversible in standard interpretations. The arrow is associated with measurement points from the pre-measurement superposition to the post-measurement definite state. Whether this is a genuine separate arrow or whether it can be reduced to the thermodynamic arrow remains contested in foundational physics. There is a causal arrow. Causes precede effects. We do not generally observe effects preceding causes. The causal arrow is, on most analyses, derivable from the thermodynamic arrow, since the temporal asymmetry of causation can be traced to the asymmetry of entropy. But the derivation is subtle, and not everyone accepts it. So we have at least these several arrows: thermodynamic, psychological, cosmological, radiative, quantum measurement, and causal. Each operates in a different domain. Each points in the same temporal direction. The alignment is total. If any one of these arrows pointed in the opposite direction from the others, the universe would be a very strange place. We would, perhaps, remember the future while the universe collapsed, or experience effects before causes while the cosmos expanded normally. Such configurations are not observed. The arrows all point the same way. The alignment is, on most analyses, derived from the thermodynamic arrow as the root. But the root itself, as we have seen, traces back to the past hypothesis, which is itself unexplained. So the alignment of all the arrows ultimately rests on a single unexplained boundary condition. The boundary condition determines the direction of every observable temporal asymmetry in the universe. Slow your attention. There is one further wrinkle to consider before we move into the closing meditation. The wrinkle is called the Boltzmann brane problem. The problem is this: statistical mechanics, taken seriously, allows for spontaneous fluctuations in entropy. Even in a high-entropy equilibrium configuration, there is a small probability that random molecular motions will, briefly, produce a low-entropy region. The low-entropy region will then relax back toward equilibrium. The fluctuation will, in the meantime, have appeared and disappeared. Now consider a very long time. Imagine the universe after it reaches heat death and continues existing in the heat death configuration for vastly long durations. During those durations, random fluctuations will occur. Most of the fluctuations will be small regions of slightly lower entropy, but occasionally, given enough time, larger fluctuations will occur. Very rarely, an entire planet might briefly appear from random fluctuation. Even more rarely, an entire brain might briefly appear from random fluctuation, with all its memories, all its sensations, all its conscious experiences fully formed in a single moment of statistical coincidence. Such a brain is called a Boltzmann brane. It is a hypothetical conscious observer, that comes into existence by random fluctuation rather than by the long chain of cosmological and biological processes that produced our own consciousness. Here is the disturbing consequence. If the universe lasts long enough, and if Boltzmann brain fluctuations are possible, then the total number of Boltzmann brains across cosmic history will vastly exceed the number of normally evolved brains. Most conscious observers in this picture would be Boltzmann brains rather than products of normal cosmological evolution. By a statistical argument, any given conscious observer, including you, listening to this, should be more likely to be a Boltzmann brain than a normally evolved brain. The Boltzmann brain problem is taken seriously by cosmologists. It is not a frivolous concern. The reasoning that produces it is straightforward, given the standard framework of statistical mechanics. The conclusion is uncomfortable. If the conclusion were correct, we should expect our experiences to be random fluctuations that will dissolve in the next moment, rather than coherent perceptions of a real external world. Our memories should be false memories, randomly produced. Our anticipations should be false anticipations, randomly produced. Nothing about our experience would correspond to anything outside our momentary fluctuation. This is evidently not what we experience. Our memories, when checked against external evidence, generally hold up. Our anticipations, when tested against subsequent events, generally prove approximately accurate. Our experiences are coherent over time in ways that random Boltzmann brain fluctuations would not produce, so the prediction that we should be Boltzmann brains appears to be wrong. The wrongness is, itself, evidence about the universe. Something prevents Boltzmann brains from being the dominant population of conscious observers. The question is, what? Various proposals have been considered. Perhaps the universe will not last long enough for the Boltzmann brain population to overwhelm normally evolved brains. Perhaps the relevant fluctuations are not possible in the actual late-stage universe. Perhaps our cosmological framework needs to be modified to suppress Boltzmann brains while preserving everything else we know. The Boltzmann brain problem connects to the arrow of time in a deep way. The problem assumes that statistical mechanics, applied to long timescales, will eventually produce all possible configurations through random fluctuation. If this assumption is correct, then the past hypothesis becomes even more puzzling, because the very low entropy initial state of our universe would be the kind of configuration that random fluctuation could, eventually, produce. The universe we observe could itself be a Boltzmann fluctuation rather than a genuinely fresh creation. If our universe is a Boltzmann fluctuation, the arrow of time is even more strange than it appears. The arrow would not be a feature of how the universe began, but a feature of a random downward fluctuation in entropy that we happen to inhabit. The fluctuation would, by the second law, eventually relax back toward equilibrium. The relaxation would be what we currently call the arrow of time. The arrow would be temporary. The universe would be drifting back toward the high entropy equilibrium from which it briefly fluctuated. This is one possible interpretation. It is not the standard interpretation. The standard interpretation holds that the universe genuinely began at low entropy, not as a fluctuation, but as a fresh state. The two interpretations cannot, at present, be distinguished by any observation we can perform. The question of which is correct remains open. Slow your attention. We are going to step back and consider what this means. Time's forward direction may not be a feature of physical law at all. Read that sentence again. Sit with it. The forward direction of time, the directionality you experience every moment of your conscious life, may not be a feature of the equations that govern matter and energy and space. The forward direction may be, instead, a feature of how the universe began. This is a strange thought. We typically assume that the laws of physics determine what happens in the universe. The laws specify the rules. The rules produce all the phenomena. The arrow of time, like everything else, ought to come from the rules. The analysis suggests otherwise. The rules by themselves do not produce an arrow of time. The arrow is produced by something added to the rules, by the initial conditions on which the rules act. The initial conditions are not derived from anything we currently understand. They are taken as given. This means that time, in its directional aspect, is not what physics gives us. Time is what the universe gives us, through a specific initial setup that physics permits but does not explain. The asymmetry of past and future is, in this analysis, a contingent feature of our universe. It is not necessary. It could, in principle, have been otherwise. What would a universe without an arrow of time look like? Imagine, slowly, a universe that began in a state of high entropy, or that began in an intermediate entropy state with no preferred direction of evolution. The equations of motion would govern such a universe, but the entropy would not steadily increase. The universe would fluctuate around some equilibrium configuration. Local regions might temporarily decrease in entropy and then increase again. There would be no consistent direction over cosmic time. In such a universe, the experiences of consciousness, if consciousness were even possible in such a configuration, would be very different from ours. There would be no consistent past versus future distinction. Memory would not accumulate in a single direction. Causation would not run one way. The universe would be, in some sense, timeless in the directional aspect we associate with time. We do not live in such a universe. We live in a universe with a clear arrow of time. The arrow is everywhere. The arrow is in every experience we have. The arrow distinguishes the moment that is now from the moments that have passed and the moments yet to come. The arrow exists because of how our universe began. It exists because of a boundary condition that physics does not currently explain. It exists because the universe somehow started in a state so improbable that since then, every motion in cosmic history has been a motion away from that improbability and toward greater typicality. This is the implication that the past hypothesis carries when its consequences are followed to their depths. Time's direction is a boundary condition, not a law. The direction was imposed at the start for reasons we do not know, and the rest of cosmic history is the unfolding of that imposition. Move with this slowly. We are now in the deepest layer of the argument. Let it settle. You are, at this moment, moving forward through time. The movement is not described by any equation in physics. The equations are symmetric. The movement is not produced by any local mechanism. The local mechanisms, the firing of neurons, the chemistry of cells, the dynamics of bodies, all inherit their directionality from the global arrow. The global arrow inherits its directionality from the initial conditions of the universe. The initial conditions are, in this respect, the source of every forward second you have ever experienced. The Big Bang's improbable low-entropy starting configuration set up a gradient. The gradient has been playing out for 13.8 billion years. The playing out has produced, among countless other things, the chemistry of life on Earth, the evolution of consciousness, your particular moment of attention to this very sentence. Each of these is downstream of the initial entropy gradient. You owe your sense of time to a single moment, 14 billion years ago, in which the universe somehow found itself in a configuration that, by all statistical measures, should not have occurred. Consider what this means for the relationship between physics and experience more broadly. Most aspects of human experience, when examined scientifically, can be traced back to specific physical mechanisms. The experience of seeing a color can be traced to the absorption of specific wavelengths of light by photoreceptors in the retina, which trigger specific neural signals, which are processed by specific visual cortex regions. The experience of feeling warmth can be traced to the activation of specific sensory neurons in the skin. The experience of remembering a fact can be traced to the activation of specific synaptic patterns in the hippocampus and cortex. In each of these cases, the experience is grounded in a physical process that physics describes. The mechanism is known. The chain from physical event to subjective experience may have gaps in our understanding of consciousness, but the physical end of the chain is well characterized. The experience of time's passage is different. The forward direction of experience cannot be traced to any specific physical mechanism. The neural processes that produce the experience are themselves directional, but they are directional only because they participate in the global arrow of time. The global arrow is what we are trying to explain. The neural mechanisms cannot explain the global arrow because they themselves depend on it. So when you experience the forward flow of time, the slipping of each moment into the past, the arrival of each new moment from the future, you are experiencing something that, at its foundation, has no fully identified physical cause. The experience is real. The mechanism is partly understood. The deepest source is unexplained. The configuration occurred. The aftermath has been continuing ever since. The aftermath includes you. The aftermath includes every conscious experience that has ever existed in the cosmos. The aftermath is what we call time. Without the configuration, no time. Without the time, no experience. Without the experience, no awareness of the question we are asking. The asking itself depends on the answer we cannot give. The very fact that you can wonder why time moves forward is a consequence of the unexplained mechanism that causes time to move forward. There is no resolution to offer here. The community of physicists has, in various forms, been working on this problem since the late 19th century. The problem has not been solved. The problem may not be soluble within the framework of current physics. Some thinkers have suggested that the problem points beyond physics, that the arrow of time may require a different kind of explanation than physical laws can provide. Whether such an explanation exists, and what form it might take, is not currently known. There is a particular intellectual humility required when sitting with this question. We have, as a species, made enormous progress in understanding the physical world. We have decoded the structure of atoms, the dynamics of stars, the geometry of space-time. We have built technologies that exploit these understandings in ways that would astonish any earlier generation. The progress has been real. The progress has been substantial. But certain foundational questions have resisted our progress. The arrow of time is one of them. The question of why something exists rather than nothing is another. The question of how subjective experience arises from physical processes is a third. These questions sit at the boundaries of what current physics can address. They may be addressable in some future framework. They may be permanent limits on what physical inquiry can resolve. We do not know. The arrow of time is, in this respect, a humility-inducing question. It reveals that something we take for granted, the forward flow of moments, does not have a clear basis in the laws of physics. The taking for granted is itself a feature of how the gradient operates in conscious experience. We do not normally examine the gradient, we simply ride it. When we do examine it, we find that it rests on a foundation that physics has not yet illuminated. Let yourself rest with what has been said. The fundamental equations are symmetric in time. The observed universe is not. The asymmetry comes from initial conditions. The initial conditions are not explained. This is the current state of the question. The state has been the same for over a century. Boltzmann was, in some respects, aware of all of this. He worked out the statistical mechanics that produces the second law. He recognized that statistical mechanics alone does not produce a one-directional arrow. He suggested in his late writings that the arrow might be a feature of the particular region of the universe we happen to inhabit, with other regions possibly having different or opposite arrows. His proposals were tentative. they have not been definitively resolved. In the century and a quarter since Boltzmann, the question has been refined but not answered. Modern formulations are more precise. The past hypothesis has been articulated more carefully. The relationship between cosmology and thermodynamics has been clarified. But the central puzzle remains. Time moves forward, physics does not say why. Now slow your attention further. We have walked through the analytical part of the question. The remaining time will be spent with the experiential consequences of what we have discussed. Notice for a moment the present. Notice that this moment is the one you are in. Notice that a moment ago was a moment you were also in, but you can no longer return to it. Notice that a moment from now will be a moment you are in, and you have not yet arrived at it. The arrangement of these three observations, past, present, future, feels in your immediate awareness like a fundamental feature of reality. The feeling is so basic to consciousness that it rarely receives examination, but the feeling, when examined, is not located in any physical law. It is located in the entropy gradient of the universe, which is located in the low entropy initial state of the universe, which is located in conditions that physics does not currently explain. There is something quietly disturbing about this once you have noticed it. You spend your entire life inside a sense of time that you take to be foundational. The sense is reliable. The sense is consistent. The sense is shared with every other conscious being you have ever encountered. The sense is, on examination, the consequence of an unexplained initial condition. The condition produced the sense. The condition has no known cause. The sense rests on the unexplained condition without anywhere else to rest. The disturbance does not produce any practical change. You will continue to experience time the way you always have. The unexplained foundation will continue to support your experience whether you understand it or not. The understanding, when present, simply adds an awareness of the foundation's nature. The awareness can be carried or set aside. It does not affect the foundation's operation. Your sense of time, in other words, is a kind of inheritance. You inherited it from the universe's beginning. The beginning sets up the gradient. The gradient produced, through 14 billion years of cosmic evolution, the chemistry that allows your nervous system to function. The chemistry maintains, moment by moment, the asymmetry between memory and anticipation. Memory exists because the chemical processes that record information work in one direction only. Anticipation exists because the chemical processes that simulate possibilities work in the same direction. The directional chemistry inherits from the directional thermodynamics. The directional thermodynamics inherits from the directional initial conditions. There is a kind of vertigo in following this chain. The vertigo is appropriate. The chain leads from your immediate sensation of nowness back to a moment 14 billion years in the past that no observation can directly access. Your experience is, in this sense, suspended over an unexplained ground. The ground does not give way. The vertigo, when felt, does not produce any practical disorientation. You continue to experience time, as you always have. The continuation is itself an expression of the gradient that the unexplained ground sustains. You cannot stop experiencing time. You cannot reverse the direction in which you experience it. You can only acknowledge that the experience rests on something we do not understand. Acknowledgement is the appropriate response. Science does not require any other action. The mystery does not require resolution. The mystery requires only honest awareness of itself. Slow your breath. The pace can continue to soften. Each second that passes as you listen to this is a second produced by the unexplained gradient. The second is not a unit of time defined by any law. It is a unit of time defined by the consistent flow of the gradient through your experience. The flow does not stop. The flow does not reverse. The flow does not vary. As long as you remain conscious, the flow continues in the same direction at the same rate. The consistency is, when examined, remarkable. The flow rate does not appear to depend on any local condition. It does not slow when you are bored. It does not accelerate when you are excited. Subjective time, the experience of duration, can vary. Boredom can make minutes seem like hours. Engagement can compress hours into what feels like minutes. But the underlying flow, as measured by clocks or any other reliable timekeeping mechanism, is steady. Steady to a precision that allows the synchronization of distant atomic clocks. Steady to a precision that lets satellites maintain their orbits over years. The steadiness is itself a feature of how the gradient operates. Where the steadiness comes from is not specified by current physics. The flow could, in principle, be variable in ways our equations would not detect. We assume it is uniform because all our measurements yield uniform results. The uniformity is so reliable that we have built our entire civilization around it. We coordinate our activities, our economies, our communications by trusting that time flows at the same rate everywhere we care about. The trust has, so far, been vindicated, but the trust is grounded in the gradient. The gradient produces a consistent flow. The gradient comes from the initial conditions. The initial conditions are not explained, so the trust, when traced to its foundation, rests on something we do not understand. This is the deepest aspect of time's mystery. The mystery does not require us to do anything differently in our lives. We continue to use clocks. We continue to schedule meetings. We continue to anticipate tomorrow and remember yesterday. None of this is affected by the unresolved foundation. The foundation operates regardless of whether we understand it. Our practical engagement with time proceeds without need for further explanation, but the engagement is taking place over a foundation that, when carefully examined, reveals itself as unexplained. The examination is what philosophy and physics do when they look carefully enough at the most familiar features of our experience. They find, beneath the familiarity, depths that the familiarity itself conceals. The arrow of time is one such depth. It is hidden by being so present. It is unexamined because it is so universally experienced. When examined, it opens up to reveal the past hypothesis, the time-symmetric equations, the unexplained boundary condition at the cosmos's beginning, the deep dependence of everything we experience on something we cannot at present explain. You are, at this moment, being carried by the flow. You have always been carried by the flow. You will continue to be carried by the flow until your body's chemistry ceases to maintain the directional processing that gives rise to your experience. The flow does not require your participation. It would continue even if you cease to attend to it. Every other process in the universe is being carried by the same flow. The stars in the sky are aging in the same direction you are aging. The planets are orbiting in the same direction time is flowing. The galaxies are evolving toward their distant futures along the same gradient. The universe is, in its largest aspect, a vast process of motion away from initial improbability toward final typicality. You are a small participant in the largest process there is. The largest process has no name. It has properties. It has consequences. It does not have a clearly identified mechanism. This is your relationship to time. You are inside it. You are produced by it. You cannot step outside it to examine it from a position not subject to its direction. You can only sit inside it, as you are doing now, and acknowledge that the inside is what you have, that the inside is what gives rise to every thought and every feeling and every experience, and that the inside rests on a foundation whose mechanism remains after centuries of careful thought unresolved. There is nothing to fix. There is nothing to do. The unresolved character of the foundation does not threaten anything in your immediate life. Your meals will arrive in the proper temporal order. Your sleep will produce dreams that proceed forward through dream time. Your tomorrow will follow today in the same direction that today followed yesterday. The directionality is reliable. It is among the most reliable features of human experience. It is also, in its deepest sense, mysterious. Let the mystery settle as something you have noticed without needing to act on. Each moment of your remaining life will be produced by the same gradient that has produced every prior moment. Each moment will slip past in the standard direction at the standard rate. The slipping is automatic. It does not require your attention. It does not require your understanding. It only requires the universe to continue doing what the universe has been doing for 14 billion years. The universe is, by every available measure, going to continue doing what it has been doing for considerably longer than your life will last. The gradient will outlive you. The arrow will outlast every memory anyone forms about you. The universe will continue to move away from its improbable beginning long after every trace of human existence has dispersed into the higher entropy that the gradient inevitably produces. This is the situation. This is the long, quiet fact about time. The fact does not require alarm. The fact does not require special action. The fact requires only acknowledgement that the experience of moving forward through moments rests on a foundation our physics has not yet uncovered. Slow further now. The remaining minutes will not introduce new analysis. They will simply give the picture time to rest in awareness as you approach sleep. The asymmetry is everywhere. It is in the cooling of any hot object. It is in the dispersal of any concentration. It is in the accumulation of any record. It is in the aging of any structure. It is in the falling apart of every arrangement that, briefly, held together. Each of these directional behaviors is, by the fundamental laws, not required. Each could, in principle, run in reverse. None of them does. The absence of reverse behavior is not produced by the laws. It is produced by the gradient. The gradient is produced by the initial conditions. The initial conditions are unexplained. Consider for a moment what it would mean for any one of these directional behaviors to suddenly reverse. Imagine a cup of cold coffee on the table beside you. Imagine that, instead of slowly equilibrating with room temperature, the coffee begins to grow hotter. Imagine that the heat appears to flow inward from the surroundings, concentrating itself in the cup without any external cause. Imagine that the cup eventually reaches boiling. The reverse process is allowed by the fundamental equations. It does not occur. Its non-occurrence is what we call the second law in everyday terms. If you saw it occur, you would not believe your eyes. You would assume some hidden mechanism, a heating element somewhere, a chemical reaction, an explanation that preserves your sense of normal temporal direction. You would not, in any case, conclude that the cosmic gradient had locally reversed. Such reversal is so unlikely, by every measure, that it has never been observed in any human's experience. Non-observation is part of what makes ordinary life possible. We can trust that cold things stay cold, that hot things cool, that processes proceed in standard directions. The trust is built into how we operate. Notice your breath. It moves in, it moves out. It does not, between in and out, pause to wait for any law to specify the direction of its next motion. The direction is given. The direction has always been given. The direction will continue to be given as long as your body operates. The givenness is, on examination, more than ordinary physics provides. The givenness is the universe's bequest to you. You did not earn it. You did not generate it. You received it at the moment of your conception, when the chemistry that would become your body first began to participate in the same directional flow that everything else participates in. You will return it at the moment of your death, when the chemistry that has been you ceases to maintain its directional processing. The flow will continue without you. The asymmetry will continue without you. The unexplained foundation will continue to support whatever further moments occur in this universe, for whatever observers may experience them, until the gradient eventually runs down to the cold equilibrium that lies billions or trillions of years in the cosmic future. Consider, briefly, what the running down will look like in cosmic time. The stars will gradually exhaust their fuel. The brightest stars will go first, in cosmically rapid sequences over millions of years. The middle mass stars will follow, over billions of years. The smallest red dwarf stars will burn slowly for trillions of years before finally dimming. After all the stars have died, the universe will enter a period in which only stellar remnants, white dwarfs, neutron stars, brown dwarfs populate the dimming galaxies. The remnants will themselves slowly cool. The gradient will continue to flatten. Eventually, even the remnants will dissolve. If protons decay, as some theories suggest, the matter constituting white dwarfs and neutron stars will slowly evaporate into radiation across timescales far exceeding the current age of the universe. After this evaporation, only black holes and very diffuse radiation will remain. The black holes themselves will eventually evaporate via Hawking radiation. The evaporation timescales are unimaginable. The largest supermassive black holes will take longer than 10 to the 100th years to fully dissolve. After all the black holes have evaporated, the universe will consist of nothing but extremely cold, extremely diffuse radiation scattered across an enormously expanded volume. This is the heat death. At heat death, the gradient finally reaches its limit. The entropy is approximately maximal. No further large-scale processes occur. Time, in the directional sense we currently experience, would no longer be operating, because the gradient that produces the direction would have flattened to its final state. This is the cosmic future the arrow of time is heading toward. It is not a future anyone alive today will witness. It is not a future any descendants of humanity will likely witness, since the timescales exceed by enormous margins the projected duration of any biological lineage. But it is the destination of the gradient. It is where the arrow points. The running down is itself the playing out of the gradient. The end of the gradient will be the end of time, in the directional sense. Beyond that end, if anything still exists, it will exist in a configuration where the past hypothesis no longer produces a clear arrow. What that configuration is like cannot easily be imagined from within the gradient. We have no experience of timelessness in the directional sense. We have only the gradient. The gradient is what you are inside of now, listening to this. The gradient is what carries each moment forward into the next. The gradient is what makes the very listening possible, the formation of new memory, the comprehension of one phrase before the next, the unfolding of meaning across the durations that this account requires. You exist as a small directional process inside a much larger directional process, inside an even larger directional process. At every scale, the direction is the same. At every scale, the direction is given by the same initial conditions. At every scale, the initial conditions are not derivable from current physics. This is the picture. This is what the analysis yields. This is what you can carry with you into sleep tonight, into the days that follow, into whatever further moments your particular gradient still has ahead of it. The moments will arrive in their proper order. They always have. They always will. The arrival has a mechanism we have not yet identified. The arrival continues regardless. That is the situation. Now let attention soften. The remaining seconds of this video will be quiet. Each second slips past. Another arrives. It too slips past. Another arrives. The slipping is constant. The constant has been with you for as long as you have been conscious. The constant will be with you for as long as you remain conscious. The mechanism behind the constancy remains, after every century of thought, unresolved. The unresolved nature of the mechanism does not interrupt the slipping. The The slipping continues whether the mechanism is understood or not. The universe does not wait for explanation before producing its temporal effects. The effects arrive. The arrival is what we experience as the passage of time. The passage is what we are inside. You can let the constant carry you towards sleep. The constancy does not require your participation. It does not require your understanding. It only requires the universe to continue being what it has been since the beginning. The universe is being that at this very moment. It will continue being that as you fall asleep. It will continue being that through whatever dreams the night brings. It will continue being that when you wake in the morning and find that the morning has arrived after the night, as mornings always do. The arrival of morning is, in its own quiet way, a small confirmation of the gradient. The gradient produced the night first and then the morning second. The order is not the opposite order. The order is the standard order. The standard order is the gradient expressing itself in your particular life. You can fall asleep now with the standard order in your awareness. The order does not require explanation tonight. The explanation, if it ever arrives, will arrive in some future moment that the order itself produces. Until then, the order continues. This is the situation, sleep. The next moment will arrive in due course. So will all the moments after that. Each will slip past at the standard rate. The slipping is what time is. The reason for the slipping is that time has not yet been revealed. Sleep